Hello everybody, welcome back to another quiz tutorial. In this tutorial, we're going to be covering quiz number 17, which deals with stress measures and stress invariance. And as you guys will see, this will be a huge part moving forward, especially when we start talking about numerical simulation. And you guys may be wondering, well, Clayton, it sounds important, yes, but I don't know exactly what it is. Well, don't worry, we're going to look into the theory and figure out what exactly we are trying to solve in this problem. So I'm going to try and keep this quiz short and sweet. The last two have been really beefy quizzes. Let's try and have a nice quick quiz this time. All right, so as I mentioned, we're trying to figure out what exactly are we trying to solve? What question are we trying to answer? Well, right now, you guys are now experts of the Cauchy stress matrix. And from that, you guys can say, okay, well, if you guys give me a three-dimensional cube that has sigma 3, sigma 1, even sigma 1, no problem. I can figure it out. I'm the smartest person alive. But the question becomes, okay, well, this is nice and mathematical, stuff like that, but what do we have in reality? Well, if I'm looking at a piece of steel, I go out to the lab and I take a nice uniaxial test, I pull the steel apart, I'm going to get a stress strain curve that looks something like this, where it's nice and elastic until it hits a certain point, which we call the yield point, and then we can see that the stress kind of increases a little bit, but not by much, and we can see that there's a very distinct change in behavior. Well, if we look back at our computer model and looking at all the mathematics of the Cauchy stress matrix, we have sigma 1, we have sigma 2, we have sigma 3, and we got three other sigmas, the shear sigma, so sigma 1, sigma 1, etc. And in total, we have 6 different values of stress. But if we look on the right, well, we only have one value of stress that corresponds to that yield point. So the question is, what is the relationship between all these three-dimensional stress variables and our uniaxial stress variable that we have on the right? Because again, when we implement a model into the computers, as you guys will see at the end of this course, we only define that curve on the right. And with that curve on the right, we can actually use a relationship between these two and figure out, okay, when does my material yield? And what happens, you guys will see, is this relationship will be dependent on all 6 of those sigmas on the left. So let's kind of get into it and discuss, okay, what exactly is this relationship? Well, in essence, we use something called the von Mises stress measure, which is also called the equivalent stress measure, because it basically takes that state that we saw on the left side, that triaxial state with all those sigmas, and it kind of converts it into a uniaxial stress state. It's a little bit more complex than that, but for what you guys need to know, that's all we're doing, is we're taking that very complicated state with all those sigmas, and we're basically transforming it into an equivalent uniaxial state. How do we do this? Well, we use a big, long, gross-looking formula. So I know you guys are thinking, ooh, this is just as bad as the partial derivatives. Well, it is and it isn't. It's long, it's scary, yes, I know. But if we look at it, it's just a function of all the sigmas. If I look in here, I got sigma 1, sigma 2, sigma 3, and at the end of the equation, I have all my shear sigmas. So sigma 1, sigma 1, etc. So if I know my Cauchy stress matrix, then I can easily figure out what the von Mises stress will be. And if I look at this equation and I say, okay, well, these are all just numbers. Well, that means that my von Mises stress is actually just going to be a single number. Now, if we look at it in its current form right now, it's very long, very complicated, but there is some simplification. And the one thing that you guys will see a lot is you guys will often be given a matrix where there's no shear. So therefore, sigma 1, sigma 1, and sigma 2, are all equal to 0. Well, if that's the case, I can cancel out that term at the very end, which is the 6 times sigma 1, squared, etc., and we have a nicer equation for our von Mises stress. As we can see, it's just a function of sigma 1, sigma 2, and sigma 3. So things are getting a little bit better. But again, what exactly are we using this for? Well, the main thing that we're going to try and solve moving forward is failure criterion. We want to figure out, okay, well, in our simulations, how can we tell the computer, or what flags can we set to indicate, okay, this material has yielded or this material is crushed, stuff like this. So 2 of the major things we're going to use moving forward, one a lot major than the other, are going to be this. So if we look right now, we have our Cauchy stress matrix, nothing special, it's just 6 sigmas. And what we can do is we can split that up into 2 different things. The first one is called the hydrostatic stress tensor. And you say, Clayton, that sounds like a pile of shit. How exactly do I figure out what this is? Well, it's actually a very simple formula. So I put that it's sigma hs, and I couldn't really find a name for this, so I just put sigma hs. But in essence, it's equal to p times I, where p is just a scalar. So if we expand it out, we have a diagonal row of P and the rest is equal to 0. And you say, okay, Clayton, well, that's not too bad, but how do we find P? Well, in essence, P is equal to sigma 11 plus sigma 22 plus sigma 33. And you're saying, wait a second, that's the sum of all the diagonal components. I've heard of that before. Isn't that the trace? Well, yes, that's just the trace. So if I want to figure out the hydrostatic stress tensor, all I do is I take the trace of our Cauchy stress matrix sigma and I divide it by 3, and that'll give us a value P. And I take that value, which again is just a scalar, and I multiply it into the identity matrix to get a diagonal row of P's, and the rest will be 0. So again, I said that one of these two major factors can be a lot more important than the other. This one is the lesser important factor, the hydrostatic stress tensor. The major one that we're going to want to look at going forward is something called the deviatoric stress tensor. So this is where a lot of the failure criterion is based around, is this deviatoric stress tensor. So if we look at this one, what exactly is it? Well, it's our Cauchy stress matrix subtracted the hydrostatic stress matrix. So if I have my Cauchy stress matrix, which is the sigma 11, sigma 12, etc., all I have to do is subtract the hydrostatic stress tensor, which is just a diagonal row of P's, and in the end, I get this over here. Now, what's so special about this one? Well, in fact, we can find the von Mises stress if we have this deviatoric stress tensor S, where the von Mises stress is the square root of 3 times invariant 1 of SS. So there's the first thing you guys are going to have to remember right there. Invariant 1 of SS, not just S, but SS divided by 2. And this is very important because actually, even though I presented them with the big long equation first, then this one, well, you guys will actually find if you go into the theory, we actually start with this one and we work our way back up to the one above. So this deviatoric stress tensor, this is where all the von Mises stuff starts come together around, if you will. It's actually called J2 flow theory, which is a lot more complex, completely out of the scope of this class. All you guys will have to remember when it comes to the von Mises stress is that big long formula, because you guys can apply it in any situation. Now, another thing we have to talk about really quick before we jump into the quiz is something called the maximum shear stress. So as you guys remember, we can use eigenvalues of a Cauchy stress matrix to find the principal stresses, which are the maximum stresses in the 1, 1, 2, 2, and 3, 3 direction. And you're saying, Clayton, that's great. What happens if I want to find the maximum shear stress? Because again, I know how to find the maximum normal stresses. What happens if I want to find the maximum shear stress? And as you guys will see, this is actually important to a different kind of failure criterion called the Tresca failure criterion, but we're not going to discuss that till later. Don't worry about it, but just know that maximum shear stress is also very important. Well, as you guys will see, is if we know the principal stresses, we can easily find the maximum shear stress, because all we're going to do is we're going to compare two of the principal stresses to each other and divide by 2. So the maximum shear stress is just simply going to be the absolute value of sigma 11 minus sigma 22 divided by 2, or sigma 22 minus sigma 33 divided by 2, or sigma 11 minus sigma 33 divided by 2. So as we can see, we have 3 equations in there. They're just going to give us numbers, and all we're going to do is solve each equation and find the maximum. Now, here's a quick little tip. The sigma 11, sigma 22, and sigma 33 in this equation, they're the principal stresses. And this is something you guys are really going to have to remember because this is such a great way to surprise students on midterms and confuse them and honestly make them get the question wrong really fast. If we give you a Cauchy stress matrix that's not diagonal, so it has shear stresses and everything like that, a lot of students will use this formula with the original Cauchy stress matrix. That will give you the wrong answer. What we're going to have to do is diagonalize that Cauchy stress matrix into the principal stresses, and then we can use this formula. You can't use this formula right off the bat. We're going to have to diagonalize and find those principal stresses first. So the second thing a question might ask, of course, is, okay, well, I know what the maximum shear is, but what are the components of my stress matrix in the case where this shear is maximum? Well, to do that, all we have to do is rotate our principal stress matrix. So remember, principal stress matrix. In this case, this would always be that diagonal matrix full of the eigenvalues. And all we do is we rotate it by 45 degrees. Well, which plane do we rotate on? I'll get to that when we get into the quiz. So this concludes the theory. And again, nice, short, simple quiz this time. So let's jump into it just so you guys can see how easy this actually is. All right, guys, welcome to the quiz. Nice, easy quiz this time, 3 questions. And as you guys will see, the questions themselves, They're actually pretty easy, not too bad. It's short, sweet calculations. You can love or ask for nothing more. Perfect. All right, so we're going to start off with question number 1. And number 1 is very nice. It says for each stress tensor, so as we can see kind of at the bottom here, we have 3 different stress tensors. It wants to determine 4 different things. The first one is the hydrostatic stress. The second one is the von Mises stress. The third one is the maximum, mid, and minimum principal stress. And finally, the maximum shear stress. So as we're going to go through these, you guys will say, okay, well, that sounds like a lot of calculating, Clayton. It is, but it isn't at the same time because the calculations are actually fairly simple. So we're going to start off with the hydrostatic stress. So we're going to have matrix A, B, and C. And what we have to remember is that the hydrostatic stress, which we call as P, is simply just going to be the trace of our sigma, or our stress matrix, divided by 3. And for those of you who forget, Clayton, well, it's been a while since we dealt with invariants. What exactly are those? Well, that's going to be sigma 1, 1 plus sigma 2, 2 plus sigma 3, 3. So it's all those diagonal components summed together, and then we're just tacking on a divided by 3. So if we go over to matrix A, which I'll come down here and I'll say P A, so the hydrostatic stress of A, well, we're going to add the diagonal components, so I'm going to highlight them. And as we can see, 2 of them are actually 0. So we're going to have 5 plus 0 plus 0. And then again, don't forget to divide by 3. A lot of students will forget that and they'll get the question wrong. So in the end, we know that the answer is going to be 5 over 3. But of course, we input them as decimal numbers. So this is going to be 1.667. And this is a stress. So therefore, it'll have units of MPa, or whatever the question gives you. So as you guys see, the calculation, really simple. We're going to come down and say, okay, well, now we're looking at the hydrostatic stress of matrix B. So again, we're just going to sum all the components. If I look at those diagonal ones there, I got 5, 5, and 0. So I'm going to come down here and say, okay, well, the hydrostatic stress of B is going to be 5 plus 5 plus 0. And then again, please don't forget to divide by 3. It'll lead to the answer being wrong. And I want you guys to have right answers. I don't want you guys to have wrong answers. So as we can see, this fraction will be 10 over 3, which is the same as 3.333. And again, it has units of MPa because it's an actual stress. Now finally, we go on to the last one. So we're going to say the hydrostatic stress of matrix C. So we're going to again add up all those diagonal components. So if I look at C, I'm just going to highlight them. We see that all 3 are the same in this case, where it's 5, 5, and 5. So I come down here and say, okay, well, my hydrostatic stress is going to be 5 plus 5 plus 5. And we divide all that by 3. Well, we can see that this is going to be 15 over 3, which is simply just 5 MPa. And that's part A. As you guys will see, it's not a hard quiz. It's actually very simple. Tedious in which we have to calculate it 3 different times, but the calculations themselves, easy peasy, not bad at all. So part B, this is where a lot of you guys will go, oh, this looks gross. This is the von Mises stress. So what I'm going to do is I'm going to write out the formula for the von Mises stress once, and then I'm never going to write it again for the remainder of this question because it's a long one, and we're going to talk about some simplifications that we can make. So we know that the von Mises stress is going to be sigma 1, 1 minus sigma 2, 2 squared plus sigma 2, 2 minus sigma 3, 3 squared. And then finally, we add on a sigma 1, 1 minus sigma 3, 3 squared. All of this is going to be divided by 2. And of course, I'm going to just finish off my square root. And I know a lot of you guys are going to say, wait a second, Clayton. In the equation in your PowerPoint, you had a plus 6 sigma 1, 2 squared plus blah, 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 blah. And you're right, that's true. But remember that the von Mises stress can be simplified into this equation if the shear stresses, I should be more specific, if all the shear stresses are equal to 0. If I come up to my matrix, and I'm just going to erase the diagonal components really quick, if we look at all the shear stresses, they're all equal to 0 in all 3 of the cases. So I don't even have to try and go to that big long formula because it doesn't apply when all these shear stresses are equal to 0. So I'll just erase these again because, again, we don't need them. And I'm going to come down and I'm going to start calculating. So if we're looking at the von Mises stress, so sigma Vm of A, we're just going to follow the equation above. So it looks really bad, but all we have to do is substitute numbers. And if you guys are third-year engineers, or some of you are fourth-year engineers, or who knows, maybe some of you are second-year engineers and just feeling brave, you guys should know how to substitute values right into the equation. So For sigma of A, our only entry was sigma 1, 1, which was 5. So what we're going to have is we're going to have 5 minus 0 squared plus sigma 2, 2 and sigma 3, 3 were both 0, so this is just going to be 0. And then plus we have sigma 1, 1 minus sigma 3, 3. So we're going to have 5 minus 0 squared. And what I'm going to do is I'm just going to finish this up. So remember, all this is going to be divided by 2. And we have to close the square bracket, or the square root bracket. And if you guys substitute all this in, you guys get 5 MPa. Now let's talk about this really quick, because this is actually something very interesting. Remember, the goal of the von Mises stress is to convert a triaxial stress state into an equivalent uniaxial stress state. And if we look at sigma A right here, that first matrix, the only entry we have is 5 MPa along the horizontal direction. So if we actually look at sigma A, it's already a uniaxial stress state. We only have one stress going in one direction, and that's it. We have no shears or stresses going in the other directions. So it's not a coincidence that since our only stress here is 5, and we come down and we find the von Mises stress, we also get that it's equal to 5 MPa. Because the sigma's already in a uniaxial stress state, we get our sigma von Mises to also be the same as that uniaxial stress state. So that's something kind of important to note, a little fun fact, if you will. All right. You guys are saying, shut up, Clayton, just move to the next question. I want a short quiz, and I don't blame you. So if we go to the sigma von Mises, it's going to be the same thing where we're just substituting a bunch of things into our equation. So now we have sigma 1, 1 and sigma 2, 2 is 5. So our first component is going to be 5 minus 5 squared. Oh, well, Clayton, that's just going to be 0. Then we have sigma 2, 2 minus sigma 3, 3. So we know sigma 2, 2 is 5, but sigma 3, 3 is 0 squared. And then we have sigma 1, 1, which we know is 5, minus sigma 3, 3, which is still 0, so squared. I'm just going to finish this up. So we know that we have to close the square root sign, and we have to divide everything by 2. And what we get is this is actually also equal to 5 MPa. And we're going to discuss why that is a little bit later in the course. So again, we can see that the sigma von Mises of A and the sigma von Mises of B are the exact same. So you guys are looking up here at these matrices and saying, okay, well, the matrices are very similar. Sigma A just has 5 in sigma 1, 1. Sigma B has 2 5s. And if we look at sigma C, it has 3 5s. So you guys are probably thinking, okay, well, if the von Mises of sigma A and sigma B were both 5, a lot of you might say, oh, well, sigma C is probably also 5 MPa. So let's come down here and find out. So we can go the sigma von Mises M of C is equal to, so I'm just going to draw my nice square root sign, and we're going to go through. So first one, sigma 1, 1 minus sigma 2, 2. Well, this is going to be 5 minus 5 squared. The second one is sigma 2, 2 minus sigma 3, 3. Again, all these components are 5, so it's going to be 5 minus 5 squared. And the last one, sigma 1, 1 minus sigma 3, 3, which again is just going to be 5 minus 5 squared. We divide all of this over here by 2. And finally, we close the square root sign. So in the end, if you guys do this, you guys actually find that sigma von Mises for 3 is actually equal to 0. And the question is, why is that, Clayton? I expected it to be 5. The other ones are 5. Why isn't this one 5? Well, if we look at this one, I'm going to highlight this in green. As we discussed in the last quiz, this is a hydrostatic stress state. And as you guys kind of remembered from the PowerPoint, we split up our stress matrices into 2 different things, a hydrostatic component and a deviatoric component. Well, if we look at this one has no deviatoric component because, again, it's all hydrostatic. And what happens is the von Mises stress is very much reliant on that deviatoric. So therefore, if we have no deviatoric stress state, well, therefore, we're going to have no von Mises stress. And that's kind of why that is. Again, a little fun fact, you guys will not have to go into too much detail. So if we look at this right here, we can see, again, it's not hard. It's just subbing in a bunch of numbers into equations. And of course, you guys are all experts at that. So we're done parts A and B. Now for part C, which I'll kind of have at the top of the screen, it says it wants the minimum, mid, and minimum principal stresses. So of course, these are 3 by 3 matrices, so we know that there's going to be 3 different eigenvalues. And those eigenvalues, of course, are the principal stresses. So all we're going to have to do is find those 3 eigenvalues, those 3 principal stresses, and we simply order them from maximum to minimum. So remember that the key to an eigenvalue, of course, is that we're going to have a matrix that's going to be diagonal. And the diagonal components of those matrices are the eigenvalues or those principal stresses. And if we look at these three matrices, we can see that the work is actually nice and easy because they're already diagonalized. So only the diagonal rows, or diagonal row, I don't know how to explain it. You guys know what I'm talking about. Only the diagonal of this matrix has non-zero values. The other ones are all zero. So if I switch my highlighter here to, let's say, let's go nice green, we can see that the rest of the non-zeros are all going to be zero. So therefore, these matrices already give us the principal values. If we were to look at matrix A, the principal stresses are 5, 0, and 0. We look at matrix B, they're 5, 5, and 0. And matrix C, they're 5, 5, and 5. So if I come down here, all I'm going to have to do for part C, I'll label it right here, part C, all we're going to have to do is label each one as the maximum, the middle one, and of course the minimum. So of course the best way to do this is find the maximum, and then you can find the minimum, and then of course the one left behind will be the middle one. You guys know how to order numbers, at least I hope you do. So what we're going to do is I'm just going to put, did I zoom in there? No, I think I'm good. So what I'm going to do is I'm going to put sigma B, and sigma C, because all we have to do is really order these. The key here is remembering that since the matrix is already diagonalized, we're given all those principal stresses. So what I'm going to do is I'm just going to put max, make a nice column here. I'm going to put min, or I guess middle. We'll do mid one next, just to kind of keep it in order. If I go max, min, and then middle, it'll just look kind of funny. And of course, we have the minimum value. So all we're going to do is go up, look at the matrix, see the three stresses, and order them from, of course, largest to smallest. So if I come up here, I say, okay, well, my maximum value for sigma A is going to be 5. And my minimum, I can't talk, my minimum, of course, is going to be 0. And it doesn't matter which 0 I pick. So I can come down here and say, okay, well, for sigma A, the maximum was 5 MPa. Well, the minimum was 5, or sorry, I can't even write either. I can't spell, or I can't speak, and I can't write. I'm doing really great. And the minimum was 0 MPa. And of course, that third value that was between the maximum and the minimum was also 0. So in this case, we also have 0 MPa as the middle one. Come up to the top here. Now we're looking at sigma B. Well, the maximum is the same as before, where our largest value is going to be 5. And we look at our minimum value, well, we find that that is equal to 0. So I come down here and I say, okay, well, the maximum value, it's just like before, we have 5 MPa. And the minimum value was the same as before, where it was 0 MPa. And the remaining value, which would be the the middle value, we can see is going to be that 5 MPa. So we come down here and say, okay, well, this one's equal to 5 MPa. So as we can see, the only hard part to this part is just finding those principal stresses. But it was nice in that the question already gave them to us. So we can finally do the same thing for part C. And if I look at sigma C, it's funny in that all three of those eigenvalues, or all three of those principal stresses, are the exact same. So in this case, the maximum is equal to the minimum, which is equal to the middle. So I can come down here and say, okay, since all three were 5, the maximum is 5 MPa. The middle one is 5 MPa. And finally, our last one, our oh my gosh, that's such a tongue twister. Our minimum one is also 5 MPa. So that's question C. It's a little bit weird because you guys may have not already heard mid principal stress and minimum principal stress. But again, all we're doing is ordering the principal stresses from minimum to maximum. It's nothing more special than that. It's a nice, easy question. So we're already at the last part of question 1. And yes, question 1 is the longest out of the 3 quiz questions. So don't be too alarmed moving forward. And what this one wants is the maximum shear stress. The maximum shear stress. And this is a very kind of funny topic that we're going to discuss a lot later. So to find the maximum shear stress, we need to find the greatest difference between these eigenvalues. So we come down here, I'm just going to write the equation for maximum shear. Oh, and we're already kind of getting close to the bottom. So the maximum shear, which I denote as tau max, is going to be the maximum difference between the following things. So the first one is going to be the absolute value of sigma 11 minus sigma 22 divided by 2. The second one, of course, is going to be sigma 1, 1 minus sigma 3, 3. It doesn't matter which order you guys do these in. A lot of you guys would have went sigma 2, 2 minus sigma 2, 3 first. And then finally, last one, of course, is going to be sigma 2, 2 minus sigma 3, 3. And I'm kind of running out of real estate here at the end, so it looks probably pretty bad, but you guys know exactly what it is. So in essence, if we look at this, all of them are divided by 2. So who cares about the divided by 2? The key here is finding what's the greatest difference between these principal stresses. So if we were to go up to the top and say, okay, well, basically what I'm going to do is I'm going to find the maximum principal stress and the minimum, and that'll be my greatest difference. So if I look at part A, my maximum is 5 and my minimum is 0. So I come down here, I can say that T max or tau max of A is going to be the absolute value of 5 minus 0 divided by 2. And some of them won't be so easy to tell which one the maximum value is, but well, actually, let's be honest. It's actually pretty easy to do. So this is just going to be 5 divided by 2, which is going to be 2.5 MPa. Come down here, we're going to say that T max of B, it's going to be the same thing. We're going to want to find the maximum and the minimum principal stress. So if we go up to sigma B, well, we know that the maximum is 5, and we know that the minimum in this case is 0. So it should be the exact same as before. We can come down here and say it's going to be the absolute value of 5 minus 0 divided by 2, which again is equal to 2.5 MPa. And finally, we can go to the last one, which is tau max of C, which is equal to, and we go up here, and we can say, okay, well, the maximum is 5, but the minimum is technically also 5 too. So if I come down here and do my equation, or throw it into the equation, more or less, I'll have 5 minus 5, absolute value, divided by 2. Well, 5 minus 5 is going to be 0, so in this case, we get 0 MPa. 0 MPa, that means that there's no maximum shear stress. And that makes sense, because as you guys remember from the last quiz, because of this case right here, hydrostatic case, there is never a plane in which there will be shear stress. Never. And that's again because it's a hydrostatic case. So knowing that the hydrostatic case and the properties of it, it's really nice in a midterm, because if you guys know that this is a hydrostatic case, instantly you can conclude that there's no maximum shear stress. It's going to be 0, as well as the von Mises stress is going to be 0. So that's another nice easy trick for the midterm. So again, question 1 was the longest. It's now over. I hope you guys realize how easy these calculations are. It's nice and easy, and if I had a PowerPoint right now, I'd put in a smiley face just to show you guys how easy it is. So that concludes question 1. Let's move on to question number 2. All right, guys, question 2. Nice, simple question. It simply wants us to compare the von Mises stress of the following matrices. So I split them up into 2 groups, Group A and Group B. As we look at part A, we have very simple matrices. We got sigma A and sigma B, and they only have one component, which is 5 and negative 5. So if we look here, they're actually the same stress matrix. The only difference is the negative sign. We come down here to part B, we have sigma C and sigma D. And if we look closely again, they're the exact same matrices, but again, we have that negative component. For instance, the first component of sigma C is negative 3, while the first component of sigma D is positive 3. And all the question wants us to do is find the von Mises stress of each one of these and compare them. Now, again, the von Mises stress, big long equation, so rather than writing it out and taking up a minute of the video time, I just included it down below. So if you guys remember from the previous question, I neglected all of this, because remember, this term right here that I just highlighted, that only applies if we have some shear stress. So if we look up at part A, we have no shear stress. We don't need to kind of include this term whatsoever. But if we look at part B, there are cases, and I'll switch my highlighter here, there are cases such as sigma C where we do have some of the shear stresses. Therefore, we're going to need to include that term. Now, we're just going to come down and we're going to solve for sigma A and sigma B first. So I'm going to say, okay, well, part A, we know that sigma A, I guess sigma von Mises of A, so let's go sigma Vm of A is going to be equal to, and our only component in sigma Vm of A is the sigma 1, 1. So we come down here, well, the first component, sigma 1, 1 minus sigma 2, 2, that's the same as 5 minus 0 squared, plus we have sigma 22 minus sigma 33. Well, both of those are just going to be equal to 0 squared. And then plus sigma 11 minus sigma 33 squared. So this is going to be 5 minus 0 squared. All this, again, is divided by 2. And you guys already know the answer to this because this was in the first question. So we know that this one is going to be equal to 5. Yay. Now you say, oh, great. Well, that's great. How about sigma Vm, or von Mises, of matrix B? So again, it's the same one as before. The only difference is now we have a negative sign on that sigma 1, 1. So if we come down here, we got negative 5 minus 0 squared plus, this one will also be 0, and plus negative 5 minus 0 squared. So I'm going to finish off my square root sign. I'm going to divide everything by 2. Don't forget that divided by 2. It's, again, something a lot of students will miss. And what we're going to find is that we're going to have negative 5 squared plus negative 5 squared. Well, you square a negative number, it's going to turn positive, and then you add them together. In the end, you guys throw this in your calculator even, you'll get 5 MPa. So I'm going to switch my marker really quick. And the big key takeaway here is that those negative signs, if the matrix is just a negative of the original matrix, the von Mises, which I'll put as Vm, is the same. So here's the key here. It's the same. Makes for a great midterm question where they'll give you the von Mises of a matrix A, and then they'll give you the same matrix, except it's all negatives, and say, what is the von Mises of this matrix? A lot of kids will go into this big, long equation and calculate it, and that's perfectly valid. You guys will get the right answer. But if you guys know this fact, oh, well, you guys can say it's just the same as A. Nice and easy. You guys are off to the races. So it's one of those things that if you guys know the tricks, it'll save you guys time. And as you guys know in midterms, time is your best friend. Now, let's see the von Mises of matrix C. So this one's a little bit longer because, of course, we have those shear components. So the first one is sigma 1, 1 minus sigma 2, 2. So I'm going to come up here. Well, sigma 1, 1 is negative 3 and sigma 2, 2 is negative 5. So we're going to have negative 3 minus negative 5 squared. The second term is sigma 2, 2 minus sigma 3, 3. So we know that sigma 2, 2 is already negative 5. Sigma 3, 3 we can see is negative 7. So I'm going to come down here. Negative 5 minus negative 7. This will be squared. Plus sigma 1, 1, which we know is negative 3. Minus sigma 3, 3, which we know is negative 7. Squared. And we're going to divide all this by 0. And the reason why I don't include the shear terms is because this is getting a little bit long. So I'm just going to include it on the next part. So plus dot, dot, dot. And continuing on here, dot, dot, dot. We have 6 times sigma 1, 2 squared. We come up here. Sigma 1, 2 is equal to negative 2. It's that component that's highlighted with the green highlighter. So we're going to have negative 2 squared. Plus sigma 1, 3 squared, which is 0, and sigma 2, 3, again, which is 0. So again, this will also be divided by 2. This is the kind of the pain in the ass with the von Mises stress, as it gets quite long. And then, of course, the square root sign carries over till the very end. And what you do when you substitute all this into your calculator, if you guys want to be brave, of course, please do it in your head. I'll never tell you to not try and do mental math. I know, me personally, my mental math is complete garbage, so that's why I don't do it, but I get 4.9 MPa. So again, the things I want to highlight here is, if we look at all the components of sigma C, they're all negative. We got negative 3, negative 2, negative 5, but our von Mises stress, of course, is going to be a positive value. So this is another key takeaway. All of the von Mises stresses that you guys will get will be positives. If you guys somehow get a negative von Mises, you did something wrong. I'll tell you that right now. It should either be 0, in the case if we use a 0 stress matrix, or it should be greater than 0. If you guys get something less than 0, then something's really wrong. Because even if we look at all the equations down below, everything is squared. So there's no possible way we're going to get a negative sign whatsoever. So we get 4.9 MPa. We come down here and say, all right, Clayton, that's great. What about sigma Vm of matrix D? And again, it has all the same components, except they're not negative anymore. They're all positive. So the first one's going to be 3 minus 5 squared plus 5 minus 7 squared plus 3 minus 7 squared plus 6 times 2 squared. And this time I was able to fit it on to a nice one clean thing because I didn't have to do so many so many negative signs, as well as I didn't include the zeros for sigma 1, 3, etc. I substitute all this in, and what you guys will get is, under no surprise, 4.9 MPa. So again, I'm going to switch to the marker. I'm going to say, well, if we look at the two, and I'll highlight them, we got 4.9 MPa for sigma C. We got 4.9 MPa for sigma D. Therefore, the von Mises is the same. So again, that's kind of the takeaway of this question, is we have to realize that the negative components, the first one, is that even though we have negative components, our von Mises will always be positive. And the second one is, if we have the same matrix, except one is -1 times the other, then the von Mises will be the exact same. As we've seen in this question, we solved it for a matrix without shear, and then we solved it for a matrix with shear. So that's kind of the main takeaway. Again, it'll save you a lot of time in exams if you guys remember that little secret. All right, with that being said, let's move on to the last question, question 3, to finish off this quiz. So question 3, I would say, is the hardest question of this quiz, because if you don't know a couple of tricks, it'll be a real bitch to solve. But it's not too bad. We're going to go over the tricks, and hopefully by the end of this, you guys will be laughing at all things von Mises. Well, at least you will be till grad school bends you over, but grad school is a different story for a different day. So let's look at question number 3, where it says, consider the stress tensors shown below. And it wants us to determine two simple things. The first one is the principal stresses, and the second one is the stress matrix in the coordinate system of maximum shear. So that's going to be the hard one, part B, the stress matrix in the coordinate system of maximum shear. But before we get into B, let's look at part A, and it simply just wants the principal stresses. So I'm going to come down here, I'm going to keep the matrix. So the key to remember is, and I don't know if I zoomed in, all right, I don't think I did, that principal stresses, so principal stresses, those are the eigenvalues. So principal stresses are the eigenvalues. So all we have to do in this matrix is find the eigenvalues, and those will be our principal stresses. So eigenvalues. And I'm going to use Mathematica. I already solved it. Again, it's a 3x3 matrix. You guys should be able to know how to get the eigenvalues if you so need. But this is a pretty ugly looking matrix. I don't got time to play around with that, and of course neither do you guys. So we just go to Mathematica, and what I find is that our principal stresses are as follows. So sigma 1, 1, which I'll call prime, is equal to 8. And of course these have units of MPa, so I might as well include that. We have sigma 2, 2, so the second eigenvalue, prime, is equal to 3.732, again, units of MPa. And then our last one is going to be sigma 3, 3 prime, which is 0.268. So 0.268 MPa. So the trick to part A is just realizing that those principal stresses, those are the eigenvalues. That's it. That's all. And what we can do down here, and we're going to do this because it's going to play a major role moving forward, is I can say that my sigma prime, because we know that there's a coordinate system that features a diagonal matrix, sigma prime, in which the diagonal entries are our eigenvalues. So we're going to say that this is equal to 8. This is equal to 3.732. And then the final one is 0.268. Again, it's a diagonal matrix, so all the other entries will be 0. And we're going to use this matrix moving forward a lot when we start considering what the question's asking in part B. And part B is kind of the new part to the quiz. That's why I didn't really spend a lot of time on part A, because part B is the new stuff, and this is where students will start maybe getting a little bit afraid or scared or lost, something like that. So hopefully I can be your guide through part B. So part B says the stress matrix in the coordinate system of maximum shear. Maximum shear. I say, okay, well, I remember that if I want the stress matrix in a new coordinate system, what I'm going to do is I'm going to call this sigma prime prime, because I don't want to relate it to the sigma above. This is going to be equal to Q times sigma times Q transpose. So we have two questions here. What is the first sigma? And I'll highlight it here. This is not the highlighting color I wanted. What's going to be this sigma right here? Is it going to be the sigma that's on the screen right now, that sigma prime? Or is it going to be this sigma right here, the original sigma that we're given? So here's the first question. The second question is, what the hell is going to be the Q matrix? Again, we need that coordinate transformation matrix Q to figure out how to transform it. So there's the first question, or I guess the second question. So once we answer those two questions, then it's just as simple as subbing everything into the formula. We're good to go. So let's talk about sigma right here. The sigma in this equation, and I guess I should make a little bit note. So this sigma right here, which I'll come over here, this sigma right here, this is equal to sigma prime. And this is something you guys will need to know because this is something I've seen so many students mess up on. This is equal to sigma prime, and that sigma prime is right above here. This is the principal stresses. So I'm going to come down here and I'm just going to put principal stresses. What else a lot of students will do, and I can't even spell stresses. I'm the one trying to critique you guys, but I can't even spell. That says a lot about me. What a lot of students will do is they'll come up and they'll use this sigma right here. And this sigma right here, of course, will give you the wrong answer. So please remember this video, remember me telling you, don't use that stress matrix. When we're dealing with this type of question where we're trying to find the coordinate system where the shear is maximum, we use the principal stress matrix, which is that diagonal matrix. So there's kind of the first key. We have to use that diagonal matrix. The second part is, how do we find Q? Well, the first thing that we're going to have to do when we're finding Q is we're going to have to figure out which plane the maximum stresses, the maximum shear stresses act on. So what I'm going to do is I'm going to come down here and I'm going to go back to my T max or my tau max equation. So remember that the tau max is equal to the absolute value of sigma 11 minus sigma 22, and this will be divided by 2, or bracket sigma 22 minus sigma 33 divided by 2. So again, these are all principal sigmas too. So please don't think that these are again from the original matrix. These will be from the diagonal matrix. And sigma 11 minus sigma 33, absolute value sign divided by 2. So what we're going to do is we're going to come through all of these and we're going to figure out the three values. So I come down here. I already figured them out. So of course you guys can just look above. You guys have sigma 11, sigma 22, sigma 33. You guys just substitute them into here. And what you guys will get is this. For the first case where it's sigma 11 minus sigma 22 divided by 2, you guys will get 2.13. For the second scenario, sigma 22 minus sigma 33, you guys will get 1.73. And then finally, for that last scenario, the sigma 11 minus sigma 33, you guys will get 3.87. 3.87. Now, if we look at this, we can say, okay, well, the maximum value is this one right here. Right here. So the key is, when we're finding that maximum shear stress, we can conclude that T max or tau max is equal to 3.87 MPa. And you guys are going, Clayton, why did you solve for that? The question didn't ask you to solve for it. And I'm going to be honest with you guys. Do I need to know what T max is? I do not. What I just did there, saying that T max is equal to 3.87, that's completely useless. The reason why I did that is because I know now that my T max comes from this right here. Sigma 11 minus sigma 33. Therefore, when I'm doing my coordinate transformation matrix, I have to consider sigma 11 and sigma 33. Well, Clayton, what exactly do you mean by that? Well, remember that our coordinate transformation matrix Q is just a rotation matrix in 3D. And we have three different cases of rotation in 3D. We have it about the x-axis, or I guess the 1,1 axis. We have it about the E2 axis, and we have it about the E3 axis. And our Q changes depending on which axis it is. So what I like to do is this, because you guys will definitely get confused. We know that in the general form, and I'll write this kind of above here, our rotation matrix is cosine of theta, negative sine theta, and of course cosine of theta. So we already know that. That's from before. You guys are experts at that. Now the question is, when we're dealing with a Q matrix that's 3 by 3, where the hell do I put those cosines and where the hell do I put those sines? So this is why I needed to figure out where tau max is. Because I'm looking at this and I'm saying, all right, it's in sigma 11 and sigma 33. Those are the keys. So since it's in sigma 11 and sigma 33, I know that my row for sigma 2, 2, or basically the second row here, is going to be 0, 1, 0. So 0, 1, 0. And then the same thing above. Clayton, where did you get that from? Again, I looked here and I said, okay, well, I got sigma 1, 1, and I got sigma 3, 3. What's missing there? 2. I'm missing 2, so therefore that row, that second row, and the second column, they're going to be zeros, and where they intersect, it's going to be a 1. It's that easy. Then all I have to do is take what I have before, the cosines and the sines, and just substitute them in. So I'm going to switch to purple, pink. I can't even tell colors now. We know that this is going to be cosine of theta, which we know in this case is going to be 45 degrees. I'll talk about that in a second. The second one's going to be negative sine of 45, which is the sine of theta. Bottom here, we're going to have cosine of 45. And then on the other side, we're going to have the sine of 45. So I'm just going to end this matrix. And the thing you guys are going to ask, how did you know theta was 45? It's kind of one of those things that it'll always be 45. Where exactly in the derivation can you find out that it's 45? Well, it's that scary thing we learned from Civ 270, Moore's circle. And of course, Moore's circle, that's a shit show. No one wants to go back to that, so you guys can just take my word that the theta is going to be 45 degrees. The key here is always trying to figure out where exactly that 1 will be. In this case, since the component we were missing was 2, 2, I know that it was going to be a 1 where the 2, 2 entry should be, and the rest in the second column and the second row were going to be 0. If sigma 3, 3 was missing, then I would have the 1 at entry 3, 3, and then of course the rest of the row 3 and column 3 would be 0. But in this case, it was 2, 2 that was missing. That's why I had this matrix. Now, if you guys don't remember this trick, the midterm's open book. Just bring in all the different cases, you guys will be good to go. So now if we go back to our equation, we know that sigma prime prime, which is what we want, is going to be Q. Well, we know Q. It's going to be sigma prime. So this is, again, the diagonal matrix. Please remember that. Times Q transpose. And you're saying, okay, Clayton, well, I have absolutely every single one of those now. So all I have to do is substitute it into the equation, and I get the following matrix. So I get 4.134, 0, 3.87, and then going to the next column, in the middle, I get 3.732. The top and bottom are 0. And then moving on to the last entry, I get 3.87, 0. And then at the bottom, I get 4.134. So I'm just going to end the bracket here. And this is my answer. This is the last part of question C. Now, the reason why I found T max is to show you guys something. Notice once we transform the matrix, we have a shear of 3.87. Well, if I look up here, I found that my T max was 3.87. So this is kind of a little trick to make sure that your coordinate transformation ended up being correct. You find that T max, which is very easy at this point, and you just look in your matrix and say, okay, my entry should have 3.87. This one does, therefore I know it's correct. And that concludes question number 3. Again, I think that the hardest thing students will have problems with is finding this Q. But again, worst case scenario, just bring in a cheat sheet full of all the Qs. You guys don't need to try and memorize all the tricks. You guys can just bring in the cheat sheet. You'll be good to go. And then the second part again is this sigma prime right here. I'm going to make another note so you guys really drill it into your heads. This right here, this is the diagonal matrix, the principal matrix. So I'm just going to put the diagonal matrix. If you guys use the original stress matrix given above, which is this one right here, and I'll highlight this one right here, you guys will get the answer wrong. So please do not use this matrix. The only thing that we used that matrix for was the eigenvalues, and that was it. So that concludes question number 3, as well as the quiz. Thank you guys all so much for listening. I really appreciate it. Hopefully this one wasn't too bad compared to the previous quizzes. And I think moving forward, they'll even get even shorter. So it's just good news on the horizon. Well, besides the midterm. So again, thank you guys so much for listening. I will see you guys in quiz number 18.